All right, so far we've learned three types of differential equations. Okay, the first one was separable. And what are these separable equations? Y prime equals the function of x times another function of y. How did we solve such a thing? Divide the gy to this side so that you get 1 over g of y, y prime equals to f of x. And then you integrate both sides by dx. That was the way to solve a separable differential equation, right? Where when you do this left side, you can perform this integration by basically making use of the u substitution, right? If you say u equal to y, then y prime dx is du, so you can integrate the left side as a function of y only, right? So you can say that during solving of the separable equation, you're making use of the u substitution. Right? That's one way to look at it. Right? So another way to say it is separable differential equation is basically applying the u substitution. Now let's think about the first order linear. In that case, you had y prime plus p of x, y, and equals to q of x. And the solution of this was first figure out what the multiplier should be. And once you calculate this, you multiply this all around. And suddenly, magically, this left side turned into the product rule of this thing, just because the way you made this. So this makes this thing exactly the same as n prime. So this entire left side became this, and you are integrating. All right. Oh, okay. I should have said this slightly differently. U substitution is like undoing the chain rule. Is that right? This y prime appeared because it's the derivative of the inside function. Right? So if you're doing U substitution, that's basically undoing the chain rule. Here, when you integrate this both sides to find the solution, so this is not done yet, but you're going to integrate both sides. And this integration cancels the prime here. So if you look at this solution, it's basically undoing what? You're undoing the product rule, right? You can say that. Okay? So first order linear is making use of undoing the product rule. That's what we're doing. And then finally, the exact equation came from where? This came from implicit differentiation, right? So it's basically undoing the implicit differentiation. So think of it this way. Any derivative technique that you learned in Calculus 1 should have some counterpart in differential equations. Because you can differentiate, of course, you can go backwards. Okay? And that backward operation is what we call solving differential equations. And that creates all these different types of differential equations for each technique that you learned in Calculus 1. So that's what's happening up till now. Right? Okay. I guess we can finish today with single differential equation. Try the following. 5x squared plus 5x squared plus 2y plus 2x y prime. Okay, let's try to solve this in two different ways and see if we can get the same answer. All right, what type of differential equation is this? It's first order, linear. It's actually, first order just means y prime. Everything that we did so far was first order. All the differential equations that we talked about so far is only first order. Okay, that doesn't say anything, but this is first order linear because all of these have power of 1. Let's try to solve this as a first order linear differential equation. Let's see, 2xy prime equals to minus 5x squared minus 2y. Oh, actually, I want this to be on this side. Okay, so let's divide by 2x. And I'm going to move this over this side because that's the format we want. Okay? So 2 cancels, and you get 1 over x y equals to negative 5 over 2 x. Now from here, what's our multiplier? E to the integral of 1 over x. So it's e to the ln of x. You get x. Let's multiply the multiplier all across. X times y prime, and x times 1 over x is 1. X times this is negative 5 over 2x squared. And then this is a product rule of something. What? It's always this thing brought down exactly as it is, except that it's the prime should be outside the parentheses, right? So you can, if you believe you correctly calculated your multiplier, you can just bring this down here and put a parenthesis, just like that. Now we're going to integrate both sides. And that gives you xy equals to negative 5 over 2 x squared plus c. And then, yeah, and then you can solve for y. You don't have to, oh, I guess you do. Just divide by x. Okay. Yes. Did I make a
Did we
mistake?
integrate negative 5?
Oh, sorry, I forgot to integrate.
Okay.
Yeah, thank you. So this should be 6. I'm sorry. Squared. So it should be negative 5/6 x squared.
It should be x cubed.
X cubed, but I divide by x.
Oh, okay.
Yeah, sorry.
Yep.
What happened to that y? After the x y prime plus y equals
What? Where? What y? This y?
not the one above
This
it.
one?
Yeah.
Oh, what do you get if you apply product rule to xy? You have two functions of x, and you're trying to differentiate by x. So the second one is differentiated, first is not. And then when you differentiate the first one, you get just y by itself. So this is exactly the same as that. Let me try to do that over here. If you have xy prime, the chain rules, and then the product rule says that's the product rule, right? Yes?
Mm-hmm.
Okay. What's x prime? What's x prime?
Wow, I have no idea.
What's x prime? Come on.
One.
1. So xy prime plus y. Right? So you see that xy prime is exactly the same as that. Right?
Mm-hmm.
So it works like magic. And that magic happened because we chose the correct multiplier. Yes?
Do we have to keep it as c over x, or can we just write it as c?
It has to be c over x because this just means it's a constant function, and this actually means something different. It actually varies. Okay. So that's how you solve using multiplier. But I actually made this so that you can solve this using exact. See, if you look at this as f of x, and you think of this as f of y, y prime, then it is actually exact. Differentiate this by y, you get 2. Differentiate this by x, you get 2. So they are equal, right? So you can solve the same thing by using exactness. Let's try that. Let's erase this part.
And just the 2x would be the xy.
Yeah, because this is how you think about it. Just rewrite y prime as dy dx, right? Rewrite y prime as dy dx, and you multiply dx everywhere. What do you get? You get 5x squared plus 2y dx plus 2x. You get 2x dy equal to 0, right? And now you can see that this should be fx and that should be fy, right? And let's skip the checking part because I just said it, right? Let's just go straight to finding the f. What is that? Integrate 5x squared plus 2y by dx. That gives you 5 over 3 x cubed plus 2yx plus 0. Okay? Plus f of y. What am I doing? Sorry, I'm almost out of time, so I'll be really quick. Okay, so then you integrate by 2xy by dy. You get x squared y. No, I don't have y here, sorry. So if you integrate by y, you get 2xy plus a function of y. So putting those two together, you get 5 over 3x cubed plus 2yx as your final harmonization of the two, and that should equals to the constant. And if you bring this to the other side and divide by 2x, you get the same exact answer. Okay? So that's sometimes you can solve the same differential equation because they belong to both categories, and both of their answers should be the same. The only slight difference here is that when you divide, your c over 2 is same as the c here. So that part, the constant part might look a little different, but at the end of the day, they're exactly the same thing.
Cool.
Okay, sorry for